misalignment, and this thing can slop around. The bad news is you hear it clanking around, and it can be a piece of junk. So it's much cleaner to just attach it, attach this shaft to that shaft with some kind of flexure coupling that's designed to pass the moment through, but can deform and flex to accommodate the misalignments without loading and breaking the motor. Okay, so that's a great application for flexures, compliant mechanisms. Okay, so these are some commercial flexure couplings. We're going to design one ourselves with FACT. Okay, so here we go. All right, so say we have this shaft. Say a shaft goes through there and the other shaft goes through there. And we're going to design the flexures that join these two rigid bodies together so that they do the job of a flexure coupling. Well, remember the first step of FACT is to pick what degrees of freedom you want this flexure to achieve. And that's sometimes the hardest part of the FACT approach, so make sure you pick your things wisely. In the case of a flexure coupling, this is the degrees of freedom you want. Okay, what you don't want is a red rotation along the axis, because the red rotation, that means it can compliantly deform with the rotation. You do not want a red rotation along that axis. You want it to be very stiff so that when this rotates, it passes that torque, it rotates right on through stiffly. What you do want is compliance in all the other directions, right? If it's slightly misaligned at an angle, you want the two rotations here, so that as the motor spins, it can go on the off-axis shaft of the other part, and you want to accommodate the three translations in all the directions. So if it's sheared off a bit, it accommodates that, or if they're not bolted at the exact distance apart you wanted, it can accommodate that as well. So these are the degrees of freedom you want. You want 5 degrees of freedom. Okay, so step 1 is pick your degrees of freedom. Step 2 is look at the FACT chart. Okay, and you wanted 5 degrees of freedom, so it makes sense to go to the 5 DOF column. Okay, hopefully we're smart enough to have not picked an independent or a dependent degree of freedom, and indeed we haven't. These are all 5 independent twists, and so it's in the 5 DOF column. So you've got 3 choices here. It's in one of these things, and there's always one right one, of course. And you can put me on pause and see, go back and tell me which of these is this one. Okay, well, you could look at this and say, well, what's 3 arrows added to each other? Well, it's a sphere, and right off the bat, there's only one sphere in here. It's right there. So you could know right away that's the right one, and take a look at it. So if we blow that up, here's the freedom space. It's basically a bunch of infinite parallel red planes with a sphere of black translation and a bunch of infinite parallel green screws, where there's screws all over the place. And notice I draw them in slightly different shades of green to show that that they can be planes of any pitches. Or I do different shades of green for different pitches. But there's no rhyme or reason to the shading here. It's just pitches of any pitch on these parallel planes. Okay, so that's that freedom space. Okay, now you might ask yourself, well, how does this? You can see how if you add these 3 together, they make the sphere. But think how do they get the rest of it? Okay, well, if you add this plus this one, you get a bunch of red parallel lines there that add all together and make this, and that makes a red plane, right? And then you could say, well, let's take this one plus this one. Well, it makes a bunch of red parallel lines that go up like that. And you do the same thing for this one. And make so pretty soon you fill in not only the sphere but all these parallel red planes. Okay. Okay. So I'll go back and show you. So that one linearly combines, and that's all the combined motions you get. So if someone says I want a flexure coupling that just gets these, you say, well, that's great. You can get those, but you also have to get all these. Okay. There's no other way. That's the linear combination of them. Okay. All right. So. Okay, so again, when you're synthesizing serial systems, oh, and by the way, when you're synthesizing serial systems, you say, what do you want? And you find the freedom space. And you notice already, this guy, the freedom space you want, is it inside the parallel pyramid or is it outside the parallel pyramid? Well, it's clearly outside the parallel pyramid. It doesn't have a constraint space. You can't design a flexure coupling that gets that freedom space unless it's serial or hybrid, right? You can't do it with a parallel system. So that's the first thing like that. Of course, that's why I picked it for this lecture, because you needed to do a serial system, and this is about serial synthesis. Okay, so then what you do once you have the freedom space is you realize, well, look, if we want this freedom space and we want to make parallel modules stacked together that together achieve this freedom space, let's break it into intermediate freedom spaces. Take this and break it into these two intermediate freedom spaces so that one parallel module will get this, one parallel module will get this, and then together they'll get that. Well, let's take this and break it. This is very easy how to break it. But let's take this, and there's many different ways you can break it. And the number of things you break off of it is the number of parallel modules. So let's say you want just 2 parallel modules stacked in series, because obviously the more parallel modules you get, the more complicated the system gets. So generally, if you're going to design a serial system, you want to only have 2 stacked stages, because 3 or more would complicate things. Now, sometimes there are good reasons to do more than 2 parallel modules, but generally it's a bad idea. Okay, so let's just break this into 2 intermediate freedom spaces. Okay, many options, but one could be, how about we take one of these from this top plane? And by the way, there's no such thing as top; those planes span to infinity. But let's take it from this plane with the translation there, and then we could take the exact same thing from a different plane, just there. So two planes, we could take those. Okay, these are 2 intermediate freedom spaces, and hopefully I can convince you that if I take, not only do these both lie within this, okay, which of course is a condition for an intermediate freedom space, but the 2 have to add together to become this. So that if you have one intermediate, parallel module that gets this, another parallel module that gets this, stack them together, you want them to linearly combine to be this. So they have to lie within it, which is obvious, they do. But do they add together? Well, students often have a hard time saying, well, how do you get the rotations from these planes to get a translation, other than just straight up and down? Well, you could take that rotation on the edge and that rotation on the edge, and by the way, there's no edge, those planes are infinitely edge, but take those 2 parallel rotations, rotate them both in clockwise and counterclockwise direction, like this, and you get a translation coming out like that. And same thing, if you take that rotation, rotate them like this, you get a translation coming out like that. So hopefully you can see very quickly, you could linearly combine these together to make that. So those are 2 fair intermediate freedom spaces that both lie within it and linearly combine to be that. You add them together, it does indeed equal that. Okay? So great. We could, and again, like I said, we just picked 2 of the same one and just located differently. They were both even oriented the same. That's okay. You could pick different ones. You could, there's no rule on that. Okay, but let's just go with this one, those 2. Okay. So then what you do is you take the intermediate freedom space's constraint space. That's just the blue plane. And by the way, you got to make sure it's in the parallel pyramid, right? You don't want to pick intermediate freedom spaces that lie outside the parallel pyramid, because you need them to have constraint spaces to synthesize the parallel modules. Okay. So we'll take this constraint space, and that's the constraint space of this. Now we're going to synthesize them. Okay, so what you do is, going back, you have this freedom space. That's the grand freedom space you want of the whole thing. Let's take one of the intermediate freedom spaces you picked, pick its constraint space, put its constraint space on there, and synthesize something that connects it to an intermediate body, say there. Again, we could use a blade because it's a blue plane. Okay? All right. And by the way, I could ask you, since it's a parallel module, is that over-constrained or not? And again, elements just by themselves are never over-constrained. It just has an order of constraint of 3. So you'd say, no, that's not over-constrained parallel module. Okay. All right. So, but now we've done one, from one stage to the intermediate stage with the intermediate constraint space. Now let's take the other intermediate freedom space, take its complementary constraint space, and connect those. Okay, and again, this is not an over-constrained module. Okay, so this isn't over-constrained, that's not over-constrained, so this whole thing is exactly constrained. Okay, this is a serial system now. It's got a ground, an intermediate stage, and a final stage. It's parallel module, 2 parallel modules stacked in series, so it's a serial system. It is not over-constrained. It is exactly constrained. Okay, the question is it under-constrained? Well, first of all, you could look at this and say, before we even answer that question, is like maybe we should over-constrain it. Maybe we should make it hybrid by putting, here's one serial limb, let's put another serial limb on the other side just to make it symmetric, because this would make for a pretty poor flexure coupling. Imagine a motor spinning that around. This is imbalanced. And if you're rocking this motor around, it's going to shake itself to pieces. So that's a piece of junk design. So this would be a good way to put your common sense in and say, well, let's make it hybrid. And trust me, when I teach you how to do hybrid, this has the same freedom space, so you're not ruining anything. You are doing the same thing as this other limb, so you are now over-constrained. So this is now technically over-constrained, but don't worry about that. We haven't gotten into hybrid. But we just did that to make it symmetric, right? But the question is this, first of all, does it work? Like, yes, it does, of course. We use fact. Fact makes things work, right? So this one can translate. This one can translate back like this, and this can translate like that, and it can rotate like that, and it can rotate like that. And it's super stiff with a moment about there. Okay, so it got the 5 degrees of freedom we wanted, and it would have if we hadn't added the other side to make it symmetric too, but it would have been weird with parasitic errors and stuff. So it's just, there's many reasons to make this symmetric and make it a hybrid. So it's not only a balanced thing, but so that it has nice, clean, no parasitic errors that are bad. But that wouldn't really matter for flexure couplings, right? You just want to accommodate the deformation, right? So, but here you see FEA confirming it works, and this does that. But again, I ask the question: is it under constrained? Okay, and it's a totally different issue of whether it's exactly or over constrained. There's a couple ways you could check it. Remember, you could hold the ground fixed with respect to the stage and see, are the intermediate bodies free to move? And yes, they are. So, it is under constrained. If I hold this fixed with respect to that, these guys can freely, like dog ears, like flap in the wind there. They're not constrained. It's under constrained. Okay? And, by the way, if you go, let's see here. Yeah, if you look at we could have told this from the intermediate freedom spaces, right? So first of all, you can see, do these two freedom spaces have anything in common? It's like, well, of course, they both have translations pointing in the same direction. These are the redundant degrees of translation, degrees of freedom, and that's why you see that flapping there. But even more so than that, we should have known from our counting trick with freedom spaces. When we picked the intermediate freedom spaces, we should have known that, like, check it out, these ones have 3 degrees of freedom in it, and this one has 5 degrees of freedom in it. So again, why did we pick 2 3-degree of freedom spaces that lie within there, and that sum together to become this, but that their degrees of freedom add together to be more than the number of degrees of freedom in this? We should have known 3 plus 3 is greater than 5, and so we should have known, and by 1, by the way, and therefore we should have known the system was going to be under constrained. And you got to ask yourself, for this example, and by the way, like, we could get, as a result, we can get twice the range here that we could otherwise. So you got to ask yourself, like, do vibrations matter in this example, or does range matter? Like, do you really need twice the range in this stretching? And the answer is no. You're not going to misalign it that badly, right? So you don't need huge range. And this is a motor, for crying out loud, that's spinning at who knows how many RPM. And so you do care about vibrations, and you don't want these dog ears, flapping uncontrollably while this motor vibrates around. So this is a bad design. Okay, we should have known from the second we were picking intermediate freedom spaces. We should have picked intermediate freedom spaces that the degrees of freedom would add up to 5. And then we would have known it wouldn't have been under constrained, and we'd sacrifice range, but we certainly don't need it here. Okay? So here is possibly a better design. I'm not saying these are great, but here's another design that falls out of fact. That's a flexure coupling that is a little easier. It's fabricatable in planar pieces that would do the trick, get the right freedom space, and have its intermediate body not be free to vibrate. These are not under constrained designs. Okay, this one, these ones is another design, but it gets even more impractical Not a good design. Here's another one that would work if you want to stare at that, how it's made in planar pieces. Here's another one, okay, that would work. And here's another one. It's just super complicated and absurd, right? But usually the simpler is the better. But all these designs would not be under constraint and would achieve those 5 degrees of freedom. They're all kind of serial designs, okay? Serial or hybrid, right? So, okay, but I'll show you later if you really are interested in finding the ideal flexure coupling. I certainly wouldn't recommend any of the ones from that case study in truth. I will, in a later lecture, give you one of the best ones. Okay, I'll tell you what one of the best, simplest ones are that works great. Okay, and it has to do with it's basically a hybrid element, but you don't know what that is yet. So, okay, okay, let's do another case study now, all the way from the top. That's super practical and goes through all the little rules you need to consider here in all its gory detail. Okay, so this is actually a desktop lathe that my professor Marty Culpepper at MIT had all of his students in a certain machine design class build. And they had certain aspects they would design and build and put together, and then they had a competition at the end where they'd cut stock on their lathe, and whoever could cut it the cleanest, the fastest, would win, and that kind of thing. So and the groups got to take their lathes home with them. So an impressive course at MIT there. So and I was the TA at the time, and so this was something that I was interested in, and the way this works here, so they were having some problems with the design. First of all, you can see here's the motor on top, and there'd be a belt that would rotate this. You'd stick your stock in there, your material, clamp it down, and this would spin. And then here you'd stick your tool cutter thing in there, and you could rotate this. And there were flexures you can see, kind of not terribly clearly, but that would guide this back and forth to move the tool into the spinning stock. And then here's the whole carriage here, and it would ride on these linear bearings. And you take this and you rotate that, and it drives this back and forth, so you can cut now along the stock here. And so if you rotate this moves that way, and you can kind of see how it works. This rotates a lead screw, okay, that has a hex nut on it that then would be rigidly attached to this carriage. So there's the lead screw, there's the carriage, there's the hex nut, and it would be rigidly attached to that carriage. And so as you rotate this, rotate the lead screw, this hex nut was rigidly attached to this, so it couldn't rotate. So as it rotated this would move back and forth, okay? And again, it was led by, you have to see that there's a flexure in here too, and there's some clearance on these things, but there was another flexures on the other side. Anyway, this was exactly constrained just by these linear bearings to just guide a nice clean translation, okay? The problem is that, and here's the structural tube it's in. So the problem is that they found in this class that if they just rigidly attached this hex nut, say just a big chunk of material, stuck it on the carriage, that the system was over constrained, and majorly, because now you have kind of this lead screw and all this stuff acting as its own kind of bearing with the linear bearings, and it's like over constraining the motion of the carriage pretty significantly. And of course, these are imperfect parts that are heavily all assembled. You can imagine in reality all these parts are slightly bent, they're slightly out of tolerance, and then you're assembling them, and you're not going to assemble them perfectly. And so if you have over constraint, it's going to be a nightmare. And it was shown, it manifests as a nightmare, and that this thing would stick and slip, and there'd be backlash, and there'd be all kinds of things that would manifest as chatter and nonsense, or stuff that was looked really bad on the stock after it was cut. So it became clear that a flexure was needed to interface the hex nut to the carriage so that it would do the job of stiffly driving the carriage back and forth as this was rotated, but would not constrain what the linear bearings were already constraining, so that it could freely move and not be over constrained, essentially. So this was a great flexure thing, and at this time I had just developed the theory for designing serial systems, And so as the T, I thought I'd take a crack at designing a flexure that interfaces the hex nut with that carriage to fix this issue. And so I'm going to take you through the design process that I went through and how we fix this problem. Okay, so the first thing is, like, let's zoom in on it. Let's think of this as the ground, the carriage, and this hex nut is the stage. Okay, and we want to connect these together with some flexure. The first step of the design process is figure out what degrees of freedom you want and what degrees of constraint you want to be constrained, right? What do you want to be stiff and what do you want to be compliant? And define those. And then that's by far the hardest part of the whole thing is what do you want, right? And particularly for this example, it was very difficult to find out what exactly we wanted, okay? I'll tell you the answers are here, okay? 2 orthogonal translations and 2 orthogonal rotations. But let me explain why that's what you want, okay? So what you definitely don't want is a rotation about this axis, about the axis of the lead screw. That means if you had a compliant degree of freedom there, you could imagine that means this hex nut could rotate compliantly with respect to the stage. That would not be good, because as you rotate this knob and rotate the lead screw as a consequence, the friction holding the hex nut on between the threads would catch those threads and want to rotate the hex nut with it. And if there was a degree of freedom here in the flexure between there and there, it would just compliantly deform and the carriage wouldn't even move. And so until it suddenly rotated so much it strained, stiffened, and then it got stiff and then it would start moving. So it would make for horrific backlash if you did that. If you had a degree of freedom rotation there, you would be going in one direction, then you'd stop, and you rotate it a few times in the next direction, and the carriage wouldn't even move. It would just deform the flexure until it finally caught, strained, stiffened, and then it overcomes the friction of the hex nut. Then the carriage starts moving. So you want this to be very stiff. The other thing you want to be very stiff is the translation. By the same token, you don't want the hex nut to be able to go forward and have that translation be deforming and not grabbing this with it. Obviously, right? When the hex nut moves, you want it to be rigidly pushing, driving in that translation direction. So the 2 most important things to be stiff is that rotation and that translation. You want them to not be degrees of freedom, which is why they're not drawn here. Those are degrees of constraint, and you just don't draw those, right? Okay, the question is, why do you want the 2 translations here, right? Well, a good way to think about it is just imagine the system hopelessly deformed. Okay, imagine the lead screw is like bent like a jump rope. Okay, it's just hopelessly bent, because in reality it is bent like a jump rope. It's just you can't see it because it's just finely bent, right? But always imagine all the errors that it could be as if it was made of rubber and it was just hugely out of whack, right? Well, if this was a jump rope and you're rotating it, then that hex nut is moving up and down and side to side. And if it's not assembled perfectly and it's not perfectly straight, which it's not, it's like a jump rope, you need to accommodate those motions up and down and side to side with high compliance, so it doesn't jam the carriage, and the linear bearings will do what they're supposed to do, right? And so you want these. And by the same token, you want these rotations, because if you think of a curved lead screw and you think of a hex nut following along a curved lead screw, it needs to rotate as it goes around the curve. Say, say this is the hex nut and it's going along a curved line. You can see this thing is rotating. And so you need rotations in both directions to be compliant, so it doesn't jam the carriage either. So you want these 4 and you don't want the other 2. Okay? So it took us a long time to realize those were the degrees of freedom we want to achieve. Then the rest of it is just kind of like follow your way through systematically the fact approach, okay? So if you want those freedoms, the question is, what's the constraint space? What's the freedom space of those 4 degrees of freedom? Well, you can put me on pause to think about it, or I can step you through here. Start doing your adding thing. What's the translation plus the translation? Well, it's a disk of translations, okay? Great. What is this translation plus that rotation? Well, It's a plane of parallel red lines there. What's this translation plus that rotation? Well, it's a plane of parallel red lines. And all those parallel lines add together to make a bunch of disks. So pretty soon you can start visualizing there's a disk of black translation arrows and a bunch of disks of red translation, or a bunch of red rotations on a bunch of parallel planes. So from that, you look at the fact chart. I mean, you can do that. That's what I do in my head to find the freedom space, but you don't need to. You can pull it up and say, okay, we want those degrees of freedom. There's 4 of them. Let's look in the 4DUF column because we're pretty confident they're all independent degrees of freedom. Okay, and let's find it. We have 10 options. Which one is it? Well, I just showed you how you could linearly combine them, and you see it would be option 8. Okay, there is your disk of translations, and there's all your other infinite parallel disks of rotations where they, there's an axis that's perpendicular to them. This one is, the axis is skewed from all the, these are still red disks, and they're all still on parallel planes, but this dotted line that intersects their center is not perpendicular to them. Here's the one that's perpendicular. So it's it has to be in here, and it's that one. Okay. Okay. So we found the degrees of freedom. We found the freedom space in the right column. That's the freedom space, and you can see it there, blown up here, and you can see here's the 2 translations you wanted, and here's the 2 rotations you wanted. Of course, there's a red disk on top and a bunch of red disks out there, and then there's a bunch of green disks of all these different pitches and everything. And it's obviously on top. These 2 dashed lines are on top of each other, right? I just don't want visual clutter, right? Okay. Okay, so you can see how the 4 lie within there, and how you get all the other ones simultaneously. All right. Well. All right. So we found the freedom space. Now step 3 is ask yourself, can you? We found the freedom space we want our flexure to achieve. Can you make it parallel or serial? Because in this case, if you could make it parallel, it would be really nice, because it's got to fit within a structural tube, and it's got to be pretty small, and you want it to be simple, and etc. So let's look at this and ask ourselves, is it inside or outside the parallel pyramid? The question is the answer is it is outside the parallel pyramid. So you don't even have the option to make a parallel version. You can't make a parallel design that does this, okay? So unfortunately, it has to be serial, okay? So then the next step is we're going to choose intermediate freedom spaces, okay? Now remember, intermediate freedom spaces have to lie within the main freedom space, okay, which means they're always going to be to the left of it, okay? So all the spaces this way are larger than that space. So if you want to find all the spaces that lie within this space, you need to look to the left of it in the fact chart, okay? And then you need to identify which ones lie within it. So it's not only things to the left of it, but they have to be within it. Not everything to the left of it lies within it. And you can go through, if you're familiar with these shapes, well, and the other thing is it better be in the parallel pyramid. Okay, so not only do you need to pick intermediate freedom spaces that lie within it and are therefore to the left of the column, but they better be within the parallel pyramid so that they have actual constraint spaces that can be used to synthesize their parallel modules. Okay, because you don't want to find, gosh, that would be terrible to find one of these that lies to the left, that lies in there, and you get it and it's like, oh, it doesn't even have a constraint space, so it's a no good intermediate freedom space. So intermediate freedom spaces better be in the parallel pyramid to have constraint spaces that you can use to synthesize parallel modules to even stack. Okay, so we're only considering things in the black parallel pyramid, and we're only considering things to the left of it. Okay, and there's a number of options. Okay, and they're boxed in red here. So you can, if you're familiar with these shapes, you would see this doesn't lie in there. None of these lie in there. This does, this hyperbolic paraboloid that rotates through. It's just there's a red line from every disk that like rotates through. So that does. This one does, because there's a disk and there's a plane of parallel red lines. None of these do. So only 2 from the degree of freedom column that are in the parallel pyramid satisfy it. All of these in the parallel pyramid lie within there, and all of these do too. And then this one's trivial, right? This one's it's empty, so of course it lies within it, right? But those are all the options. If you have a difficult time